Hooke's law for springs, rubber bands, and other elastic materials. Robert Hooke was one of the most renowned scientists of the English Enlightenment. In addition to working out the behavior of springs and elastics in 1660, he went on to invent the microscope to investigate the world we could not see. He discovered and invented the term for the cell. This means he wrote the first European scientific bestseller, The Micrographia, and in addition to being a brilliant mathematician, physicist, and biologist, he naturally spent a whole lot of time ticking off Sir Isaac Newton, the other brilliant English physicist, mathematician, and giant ego of his time. Hooke looked at the way things stretched. He saw that if you stretched a spring with 1 newtons of force, yeah, it stretched. But if you stretched it with 2 newtons of force, the distance doubled. With 3 newtons, the distance tripled. With 4 newtons, the distance quadrupled. And by this time, Hooke was pretty much sure what pattern he was seeing. Sooner or later, of course, the spring broke. And that was that. We call springs that obey Hooke's law well-behaved springs, or sometimes springs. We call springs that do not obey Hooke's law broken springs, aka you stretched it so far you broke it, doofus. Hooke's law describes the left portion of the graph over here, where springs and rubber bands stretch and unstretched by a direct proportion. Anything after you've begun to warp the material is non-Hooke's law and isn't covered by this principle. Hooke's law was published in Latin as ut tensio sic vis. He published this as an anagram in 1660, secure in the knowledge that if you couldn't figure it out, you couldn't steal his copyright. Fortunately for us, he published the solution, still in Latin, in 1678, by the time everybody knew that he had invented it, and went on to argue with Isaac Newton about which one of them was going to figure out gravity first. Said in algebra rather than in Latin, as you stretch it, so goes the force. Force and stretch distance are directly proportional. Where F is the applied force, we'll call it the spring force in newtons. K is the spring constant in newtons per meter, and X is the stretch distance in meters. Actually, that ought to be delta X because it's the stretch distance from equilibrium. Take where it is now and subtract off the original length of the spring if you're doing this in lab or you're the slightest bit confused. We're going to call it X in this class mainly out of sheer laziness and the desire for a clean page. If there's any doubt, you know how to find the stretch distance. It's stretched from equilibrium, not from 0, simply because I've never seen a spring that is 0 centimeters long. Quick check, lowercase k is the spring constant, not to be confused with uppercase K, which is kinetic energy. When in doubt, check the unit. The spring constant is measured in newtons per meter squared. Kinetic energy is measured in joules. As we learned when we talked about spring potential energy, the spring constant measures how stiff the spring is. Larger the spring constant, in hundreds of newtons per meter, the stiffer the spring. You may be able to see this by checking out the graph. If you pull it, and it takes a tremendous amount of force just to move a little bit across the x-axis, that's a very stiff spring. This one can go a lot farther with the same force, and this one requires very little force to go anywhere at all. Many things have a spring constant, not just metal springs. All sorts of materials display some sort of stretchy behavior. Quick check, which has a higher spring constant, the rubber band or the car suspension? If you said the car suspension, you're in good shape and you remember what K is. So going back to Hooke's law, please note that the boldface here, F and X, means that these guys are vector quantities, and that means that we're not done unless we check the direction. The direction of the spring force is opposite the stretch distance. Hooke's law is sometimes written F equals negative kx. Please note the color code. This negative is not a minus sign. It does not go into your algebra. You do not plug negative kx into anything. This negative goes on your free body diagram. If you stretch the spring to the right, F goes to the left. If you stretch the spring down, which is negative, two negatives, negative x makes a positive and F goes up. Don't do that algebraically. Just do it in your head. see which way X goes, and pull F the other way. F is called a restoring force because no matter which way you pull, it pulls the other way. And you noticed it, it's also a smart force because no matter what you do, it will oppose you almost, on a scale of mechanics, instantaneously. Quick fill in the blank in your head to make sure you know what you're talking about. Can you read this sentence? Can you decide stretch or compress, positive X or negative X? Pause, give yourself 5 seconds to think, and when you're ready, press play. Check. Hooke's law, the compression or the lengthening of an ideal spring from equilibrium, X equals 0, is directly proportional to the applied force F. You pull Kx, that's directly proportional to X, and pull the other way. If you're stretching, there's your force, X is positive. If you're compressing, there's your force, X is negative. More X, more stretch, or more compression. Next example, again, see if you can read through it in your head. Pause 5 seconds later. When you're sure, press play. Hooke's law is often written F equals negative Kx. This is because it describes the force that the spring itself exerts on the object that's attached to it. The negative sign indicates that the direction of the spring force is always opposite to the displacement of the object. Equilibrium position, compression gives you negative X, and you have to pull this way. That's why the spring pulls that way. You push left, the spring pushes you right back to the right. For stretching, that's positive displacement. You pulled right, the string pushes you back to the left. Now, this is an example that's worth trying in your notebook. So right under your notes, do a quick sample problem, work out the sample problem, press play when you're ready to check your work. There, that wasn't so bad, was it? Please tell me you didn't get stuck. All right, if you did get stuck, make a laundry list of the information you know. You know the force, you know the spring constant, you don't know X. So set up your equation, plug, chug, 4.6 times 10 to the negative second meters, aka 4.6 centimeters. Not bad for an 8.7 Newton weight. Next example. Find the spring constant. First step in any remotely useful lab, anywhere ever. Find the spring constant. Take a look at the lab data, solve for the spring constant, plus play to check your work. All right, this one actually required some thought. The spring is 0.38 meters long. That means you had 4 centimeters of stretch distance. Plug, chug, solve. Spring constant of 50 newtons per meter, which is very, very flexible and light. Reading graphs. Spring A, spring B. Describe them. Do a quick sketch of the graph, label them, describe which spring is which. Press play to check your work. Ready? Well, let's see. There's our force. There's our force on spring B. There's our force on spring A. And it's clear then that A has stretched a lot more than B. It's gone farther from the same force. Which spring is stiffer? Spring B, because it's harder to move. Now, how does stiffness relate to slope? Well, stiffer spring is associated with the greater slope and the larger spring constant, which makes perfect sense when you look at the formula. Conclusion. Intro to material science. You declared your major 3 years from now, but you heard it here first. Words of the day, elastic and plastic. Elastic means something that returns to its original size and shape when you let go. Stretch it, deform it, pull it any which way, every which way, let go, it goes right back to the way it was before. We call this a reversible deformation because whatever you do, it can be undone. Plastic, on the other hand, plastic is a material that once you warp it, pull it, twist it, or bend it, it stays in that shape and never returns to its original shape. This is an irreversible deformation. Once you change it, it doesn't change back. Think every plastic grocery bag you've ever stretched and warped as an example. Fact: nothing is elastic forever. If you apply too big a force, the material will lose its elasticity. Hooke was specifically concerned with the left half of the graph, elastic materials undergoing regular elastic behavior. Once you stretch it long enough, you stop seeing elastic behavior and start seeing plastic behavior. Hooke's point is that every material has some elastic behavior and some plastic behavior under different conditions. Under normal conditions, certain behaviors predominate. We hope you have enjoyed Hooke's Law. You will study it much more in later years in the lab, and we will play with some nifty calculus tomorrow. After all that math, we will discover why a spring goes boing.